It is my pleasure to introduce our next speaker, Razvan Teodorescu from the Department of Mathematics, University of South Florida. The title of his talk is Connectivity Bounds in Quantization on 2D Domains.
Thank you. Thank you very much for the introduction and for the opportunity to speak at this event. I think this talk should fit quite well the general theme. It is, as you will see, indeed a problem that comes from quantization, but however is intimately related to geometry and harmonic and conformal analysis, while at the same time having a strong geometric component. So let me start by defining what this problem is about. We are looking for a domain in complex plane, which is assumed to be bounded and with a finite number of boundary components, so a finite connectivity, on which there is a requirement that there be a well-defined quadratic differential representing, from the point of view of conformal field theory in theoretical physics, the quantity known as holomorphic stress energy tensor, or a two-dimensional quantum conformal field theory. So this quadratic differential has to be well defined on the domain, and by extension on the Riemann surface, for which this domain is a uniformization domain, along with connection forms, so differentials in the canonical sense, that on the boundary components provide representations for the Lie group U1. That's because for a full quantum theory, that is beyond just the quantization itself, but takes into account the geometry of the manifold on which it is defined. There has to be a symmetry group, a group of continuous transformations, and in the simplest case, and in the case of two-dimensional manifolds, the basic choice would be U1. So furthermore, the last requirement is that the quantity which you obtain by taking the product between these two first-order differential operators, denoted by del here, behaves in a manner consistent with quadratic differentials, and I will define that fully on the next slides. It is known as a projective connection, especially in the geometric Langlands program research. So with all of this, further requiring that on the boundary components, this quadratic differential provided by the stress energy tensor is expressed through invariance of the Riemannian metric on the boundary, we have sort of a two-dimensional Yang-Mills problem, a toy model, in which geometry, quantum theory are all implemented at the same time. And I will announce right away that the solution comes rather unexpectedly from translating this problem into the language of functional theory and, let's say, harmonic analysis in the sense of its relation to complex analysis. And the answer is that for all of this to be possible, the domain omega must be what we call extremal for analytic content. And again, that will be defined on the next slide. But just to continue with announcing the solution will be explicitly written by realizing this density of the stress energy tensor as a second-order derivative of an analytic function denoted by capital phi here, and those connection forms on the boundary being simply basically the tangent vector, unit vector, on each boundary component. Now, along with this solution, we will obtain another set of faithful representations of U1, which are the functions denoted by Vk, and which, in the sense of quantum theory, are chiral fields. They will be associated with a definite orientation of the boundary component on which they are based. So all of that will come about by translating the problem as an extremal problem in function theory. But even though I have given these details, a question still remains, and I will answer that towards the end of the talk. Just how constrained is the geometry of such a domain now that we know that this is the answer? Just to double check, you can hear me well, correct?
Yes, we can hear you.
Thank you. So let me go through the list of defining those elements I have already outlined. We switch gears for a little while. The classical analytic content problem for domains in C, but it's easily extended to higher dimensional complex geometries, is a problem of, strictly speaking, of approximation theory, in which we start from a compact set, K, denoted as K here, and we denote by C of K the algebra of continuous functions on K with the uniform one, and by R of K the subalgebra of the closure in this algebra of continuous functions of the set of rational functions whose poles are in the complement of the compact set. Then the analytic content of this compact set, and along with it, the best approximant, denoted by this curly phi symbol, are defined in this optimization form. Lambda is the infimum in the uniform norm of the difference between the anti-holomorphic variable z bar and the function from the subalgebra of rational functions, while phi is the unique solution that realizes this analytic content. And just to give two and easy to understand, and actually the only two easy to understand examples, one of them is you take an annulus, so two concentric disks, one of radius R1, one of bigger radius R2. The domain has connectivity 2. The best approximant is basically the function 1 over z, which is obviously analytic in the annulus, and the analytic content is simply the difference between the two radii. If you send the smaller radius to 0, you get a whole disk, a punctured disk, obviously, in which the analytic content equals the radius itself. And another simple example, let me go here, it's actually a singular case. You can get the analytic content to be 0 if and only if the closure of the rational function set is the whole algebra of continuous functions, and then by strong Weierstrass, the distance will actually be 0. So what's important about this part of the theory is that there was already a lot of work done long before I looked into the problem that we're discussing. And eventually I joined forces with a group that was searching the following problem that was still an open conjecture in that area. It is known, this is again a rather old result, at least 40 years or so, that for any set described as before, that analytic content has a lower bound equal to the ratio between twice the area divided by the perimeter. We take an infinity if the boundary is not rectifiable from the lower bound, and from the upper bound, the square root of the area, basically. And an immediate application of this set of inequalities is the well-known isoperimetric inequality relating area and perimeter. So to solve this problem, again, it took a considerable effort, and eventually it was achieved in this reference number 1 here. The article appeared about 7 years ago. In order to solve the problem in kind of a reverse engineering way, the equivalent formulations that provide you with a characterization of a domain that's extremal for analytic content were understood as being precisely the content of the 2D animals problem that I'm presenting about. And here's what I mean by that. The following are equivalent for any bounded domain extremal for analytic content in the complex plane. with the finite number n here of boundary components denoted by gamma k, gamma I, gamma j, um, with the rectifiable boundary. So what's important in this um, list of equivalent results basically is the reformulation through items 3 and 4. So the moment you have a domain that's extremely pointed content, then on the boundary, that best approximate phi satisfies the following rather geometric constraint. Its deviation from the anti-holomorphic variable z bar happens to be proportional to that parameter lambda, and the content itself, and oriented along the normal direction. So it's basically the normal vector scaled out by precisely the analytic content lambda. And that's going to be true. It will hold true on every one of the boundary components. And I call it a Riccati equation because taking one more derivative in the holomorphic variable of this identity and then extending it into the domain becomes a full-blown Riccati equation for the analytic continuation of the functions that happen to be unit vectors, tangent vectors on the boundary component. And the second equivalent formulation, which comes from this Riccati equation I have just described, is the well-known reformulation as a second order let's put it this way. The Riccati equation can be understood as a compatibility condition for a first order vector ODE. This is the second order vector ODE, not vector ODE, complex scalar ODE that is equivalent to that linear vector ODE, first order ODE. And that again has to be satisfied by every one of these functions v1, vn, every one of them associated with one of the boundary components on which they have constant modulus 1. The equation itself being pretty much the canonical form, and for every one of these functions, that scalar term in the differential operator being proportional to the derivative of the best approximate phi prime. So we start to convert these results back towards our quantization problem by the following observation. Given an equation of this type, like at item 4, it is a classical result of differential equations that for any two such solutions, let's say v1 and v2, the scalar term here, phi prime over lambda squared, happens to be equal to the Schwarzian of the ratio of those two solutions. Schwarzian derivative is defined here, and it's making a natural appearance in the theory of quadratic differentials in the first place. And I recall what that means. If you have a quadratic differential on a Riemann surface, one of the ways to test that it is one is that under a conformal transformation, let's say from z to zeta, given by the conformal map F, the quantity, in this case, it happens to be a differential operator, but whatever the density of the quadratic differential is, must transform according to this law. So it's going to be very trivial identity when the Schwarzian of the conformal map is 0. And that is another known result in complex analysis that is a way to characterize the elements of the Möbius group, the global conformal transformations of the whole Riemann sphere. But if you are not looking at a Möbius transformation, then the Schwarzian is not going to be identically 0. So by providing this kind of translation between the two formulations of the problem, we arrive at the following realization. If we have an external domain omega, satisfying all those conditions, then this second order differential operator that's constructed through the derivative of the best approximate is going to be a projective connection on the domain. And the function solving the differential equation what item 4 here, every one for each boundary component satisfy precisely the conditions imposed to the chiral wave functions of the original Yang-Mills problem. They are given explicitly by these exponentials in which we integrate starting from a point on the boundary, going either along the boundary or into the domain. The unit vectors UK, which are basically the conjugate of the tangent vector along that curve, if necessary, continued into the domain. And because they are chiral, because it's a simple exercise, when you go ahead and integrate in this exponent with respect to the arc length, that is a more natural way of writing this integral, then what one realizes is that the decomposition of the projective connection here as a product of two first-order differential operators will make it so that either one or the other of the two factors of the product will identically annihilate the function vk. One of them will annihilate the functions that are defined starting from the boundary components, let's say, inside the domain, and the remaining one will be associated with the outer boundary component. So let me go a little bit faster over these details. Let me, just a second, go straight to the interpretation, and then I will give a few details on how exactly the resolution comes about. So the problem I formulated in the beginning, which is a proper Yang-Mills problem, conformal field theory, compatible with the Riemannian geometry that is specific to that domain, has a number of different interpretations, which I will give in a moment. And again, just to note, on the boundary component, in every one of them, the reduction of that quadratic differential happens to have a density that is constructed out of the only Riemannian geometry characteristics of a planar curve. So it has the form 1 plus lambda times kappa, where kappa is the geodesic curvature at that point. And all of these are positive definite, so to speak. So what I said in the a moment ago about the interpretation of this solution through equivalent forms of quantization is represented on this slide. If we have a domain extremal for analytic content, as I have described, then by introducing a vector potential in 2 dimensions, this vector function A of x and y, satisfying the gauge condition of zero divergence, and subject to the boundary condition that along each boundary component it is a tangent vector of constant magnitude lambda, then the solution to this problem, which is a semi-classical version of the Yang-Mills problem that I started from, provides a complete parallel to what I was describing earlier. For example, the extremal domain condition satisfied by the domain itself, the externality condition satisfied by the domain itself, is basically nothing else than an application of Green's theorem for this vector potential on the domain omega. Projective representations Vk that I provided earlier, which are again the exponentials of those integrals along the boundary component or continued in the domain, in this case of the gauge field, are naturally associated with an optimization problem because, as one can easily see, taking the derivative in this function Vz and restricting it to the boundary, the optimization, minimization of the distance between z bar and the best approximate is exactly the same as finding the extreme of the norm of the generator L minus 1 in the group of Möbius transformations, the simple derivative. So now let me just give you very briefly a glimpse into how the whole proof goes. It rests on a classification of quadratic differentials on finite genus Riemann surfaces provided by indifferent, through different results by Jenkins and Strebel. And we can make use of that classification by applying, to begin with, the Liouville-Green approximation technique in expressing the solution to that second order differential equation that I showed. When one does that, the natural object that is used in the ODE theory is the so-called Stokes and anti-Stokes graph of the equation, which is consisting of arcs starting from a given point, point that's in the domain or on the boundary, z naught, subject to the condition that along the Stokes arcs, the imaginary part of this integral is constant equal to 0, and for the anti-Stokes graph, the real part is constant equal to 0. And these arcs are analytic. They are disjoint except at those meeting points, which have to be turning points for the differential equation itself. So once we start looking at the problem in the language of this Stokes anti-Stokes graph analysis, then it becomes possible to establish the fact. This is rather a technical, analysis type inequality-based proof that the quadratic differential phi prime dz squared, while on the one hand clearly strictly positive definite on the boundary, it cannot have any zeros in the or any of the boundary elements as well. And again, that is done by again, very brief overview over this, using the Liouville-Green formula for the asymptotic expansion of the solution, and assuming that there can be a zero on the boundary, then eventually one arrives at the contradiction with the fact that, as I showed earlier, the overall, the quadratic differential is positive definite on every one given boundary component. So that eventually, I'll skip the interest of having managed to get the end, that in turn, through the classification provided by Jenkins, allows to identify a domain that's extremal for anti-content as being maximal in the sense of Jenkins, and that was a well-known fact since the 60s, that such a domain cannot have connectivity larger than 2. Which, of course, with one more simple proof, turns out to be equivalent to the domain being either a disk or an annulus, the example that we started from in the first place. So now let me just give you in closure some kind of interpretation from the point of view of conformal pure theory or two-dimensional Yang-Mills theory, what this is actually saying. It's that when you have the annular geometry, it's very easy to actually solve those equations with elementary means. There are only two solutions, one for each boundary. In this, on this page, I represent by R1 the smaller radius and R2 the larger radius. And the two solutions are obviously defined in such a way that they are analytic. One of them on the disk of radius R1, and the other one on the complement of the disk of radius R2. And they, when implemented on the boundary curve itself, all they do is that they provide for us uniform winding numbers around the circles. So by, say, in this formula, setting z to be r2 times e to power I theta shows that for this function to be single valued, we need to have the radius r2, and by the same analysis, the radius r1 here, an integer multiple, positive integer multiple of of lambda. So the quantization that we started from in the highest generality sense turns out to be associated with a very direct quantization of all these lengths that characterize the domain. In particular, the two consecutive radii have to be multiples of lambda. And in this solution, there are actually consecutive multiples of lambda. In just to, let's say as a cost analysis of the whole exercise, one can look at the group of conformal automorphisms of such a domain, the annular domain, and assuming that this length parameter lambda has been fixed, which means we do not allow for dilations, all that is left is rigid rotations and inversions with respect to a mid-circle of radius square root of R1, R2. This second transformation maps each boundary component into the other with the corresponding orientation, and each of the two solutions, V1 into the other, likewise. One can easily think, once the solution is known, back in terms of the original problem and ask the question whether perhaps approaching the problem by relating it to the group of automorphisms of the domain wouldn't have been a little easier. And I say that because if you have a domain of connectivity greater than or equal to 3, it's again a well-known result of conformal field theory of complex analysis, that the group of automorphisms is finite. It cannot contain any Lie subgroup, and that would have been a rather non-constructive way of deciding from the very beginning that the domain must have connectivity bounded by 2. And I think I'm right on time, and I welcome any questions you might have.
Thank you.
Thank you.
Any question to the speaker? If not, let us thank the speaker again. Our next talk will start in 1 minute.